This talk will be given by Laxman, scaling parallel algorithms to massive data sets using multi-SSD machines.
Thanks, Cliff. So I'm speaking last. Is it too loud? Is it okay? I'm speaking last so I can go over. No, I'll try not to do that. So today I'll be talking about our recent work. This is a SPA 25 paper on scaling parallel algorithms to massive data sets using multi-SSD machines. This is a work that was led by my student Peter, shown on the left here, by Jamshed, who's now a postdoc at Northeastern. And yeah, I'm from UMD. This work was done while we were at UMD. And I also work with the folks on the graph mining team at Google. I want this to be kind of like an interactive talk. Like this talk is kind of out there. It's not usually like the kind of work I do. So it was kind of a very exploratory project for us. And we're still kind of exploring and figuring out how this system and this setting works. So this is a slide I used to show a lot. I think this is from my PhD thesis defense. And the point was that these multi-core shared memory machines, I don't know if any of you have looked at like a server, but a server looks like this. It's kind of like pizza box, maybe a bit bigger than a pizza box. It's quite heavy. And back when Guy, my advisor, bought this server, it cost about $20,000, and that was like the cost of his Nissan Leaf. But I claimed this was affordable. And since then, you could buy this exact server for much cheaper. You go on eBay, you could buy it for like $3,000 now. And why do we care? Well, these single machine multi-core servers are extremely powerful. You can get servers with hundreds of cores, terabytes of memory. And this is the numbers that we had for AWS at the time. You could actually go rent a server with like 24 terabytes of memory. But one thing I didn't say in my defense is that this is really, really expensive. If you wanted to buy this machine, it would cost you like $150,000. And the main cost is the DRAM. The DRAM is extremely expensive. I guess the exact amount depends on the exact DRAM prices of the day. So what if we have some nice algorithm and we want to run it on a big input and we just are out of memory? Well, you can buy more RAM, but as I said, that's going to be very costly. And it might require other system changes. You might have to buy a multi-socket machine to have enough slots for your DRAM sticks. Or you might need to go use distributed computing, which is a problem for other reasons that Kuba mentioned in the talk that started this workshop. So the moment you start hitting network, you're going to be paying for network overheads. And although NICs are getting faster, they're still quite slow compared to everything you could do locally within a single machine. So this raises a natural question. Maybe we can just kind of extend the domain of like single machine techniques by using disks. So maybe we can just switch to using disks to store even more data that won't fit into RAM. So if you go look at prices on Amazon, things seem very promising. So a DRAM stick, 64 gigabytes of DRAM, you could buy this for about $100. But with the same amount of money, you could buy a hard drive with 8 terabytes of capacity. That's looking really good. We can maybe store really large amounts of data. So with a similar amount of money, you can get 128 times the capacity. But is this too good to be true? Unfortunately, it kind of is. So this is designing algorithms that can work well on disks is called the external memory setting. And so this is extensively studied in the 80s and 90s, and it's still an ongoing topic. And in principle, you could use these external memory algorithms to handle extremely large data sets at low cost, because you could just store the data on these disks. However, these algorithms in practice tend to be kind of slow. And the reason is that disks are slow. And that hasn't really changed despite all the advances in technology. So disks are still pretty slow. And I'll show you some numbers on the next slide. But what about using solid state devices, right? SSDs. So SSDs are much faster than HDDs, hard disks, but yet they're much cheaper than RAM. So if we use the same $100 budget to buy an SSD, you can go from 600 megabytes per second, which this is the bandwidth you're getting from a disk, all the way up to 7 gigabytes per second for a single SSD. That's like a 10x improvement in bandwidth. However, you're losing some capacity. So you're going from 8 terabytes to 2 terabytes. So you're losing, you're only getting a quarter of the capacity, but that's not too bad compared to this performance improvement. Now, compared with RAM, we're still highly cost effective. So we're still getting like like 50 times the capacity with the same budget. So that's a pretty good deal. But the bandwidth is potentially much lower. So on our machine that I'm going to show you in this talk, the aggregate RAM bandwidth is about 145 gigabytes per second. But a single SSD is only going to give you 7 gigabytes per second. So there's still this large performance gap between between what you can do in RAM and a single SSD. So what's the natural thing to do? Let's just use multiple SSDs. So what if we attach multiple SSDs to a machine? Each of these SSDs gives us 7 gigabytes per second of bandwidth. And these numbers are from using PCIe 4, if you know what PCIe is. So this is the 4th generation of PCIe. And in principle, the more SSDs you add on, the higher the aggregate bandwidth gets. So we could go all the way up to a pretty large amount of bandwidth. So this seems pretty straightforward, right? You just replace your RAM with SSDs. But what actually changes? Well, a lot will have to change. First, in terms of machine configuration, how do you actually do this? How do you attach a lot of SSDs to a machine? What if your machine doesn't have enough PCIe slots? Okay? How is the data stored? How is it accessed on the SSDs? Do you mount a file system on the SSDs? Do you treat it like a raw block device? Do you access all the SSDs separately, or do you map them into a single virtual device using something like RAID 0? And there's other nitty-gritty low-level details, something called IOMMU for those of you who have heard of it. And all these choices can cause problems, and these are like foot guns that you can shoot yourself in the foot when you're building a system. And then on the algorithm design and implementation side, once you've actually built the machine, what do you do? So can you just run your shared memory algorithms on a multi-SSD setup? It seems tricky at first glance, because reads and writes need to happen at larger page sizes. SSDs are still, you can't do byte level, you can't just access cache lines. You need to load 512 bytes or 4096 bytes at a time, depending on the exact SSD model that you're using. And even if you do make IOs of these small sizes, the best bandwidth you can get with the lowest CPU overhead comes with very large IOs, and you prefer sequential IOs over random IOs to some degree. And finally, SSDs have internal parallelism. So if you're just issuing one read or write from an SSD at a time, you're not going to actually get and saturate the bandwidth for that SSD. So you really want to be queuing multiple reads and writes per SSD. So this raises the following questions that we had. Well, one, can we just build one of these machines? Can you build a multi-SSD machine with a lot of SSD capacity and get high bandwidth from it? And can you do this in a way that's significantly cheaper than the corresponding DRAM-only machine? And once we built the machine, well, can we design algorithms, external memory algorithms on multi-SSDs that are almost as fast as their shared memory counterparts? So when we go from, let's say, a shared memory sorting algorithm to a multi-SSD one, how much performance do we lose? Can we limit that? And finally, by offloading this way, can we actually extend the range of dataset sizes we can process while using a very limited amount of DRAM? This is like the original promise or the goal of an external memory algorithm. So any questions before I go on? Siddhartha.
One question, I don't know if you have any numbers on this, but this persistent memory stuff that Intel was working on, I would imagine that falls somewhere in between in your graph between the DRAM and the SSD. Do you have any idea where it falls in that trade-off? Or?
I don't remember the exact costs off the top of my head, but in terms of capacity, I think it was more capacity per stick than a DRAM stick. But the cost was pretty high, right? Sorry, can you?
It's more expensive than regular DRAM.
Good. So for the audience, it's more expensive than the DRAM sticks.
But you get 8x on the capacity.
8x capacity, but the costs were high. And that technology, as of right now, is not being developed, right?
Yeah. So your goal is to identify the right applications, the appropriate applications for this new setting, or is it to have a general kind of computing platform where you can do random accesses in data and don't brain core fetch or have data in pages and all this, like the block accesses, right?
So the question is, well, what is our goal to kind of explore this setting, or to show some applications that can benefit from it? I would say that,
for instance,
yeah.
a B-tree, right? A B plus tree or something. If you have a B plus tree and you want to implement it in this setting, because the nodes of the tree are of page size, then it might be okay. If you want to do general computation, then it's not okay.
Definitely. So I guess our goal is we haven't seen many papers exploring this. There's been some work on the database side. There's some folks in TU Berlin who are working on databases. But the patterns and types of workloads they have are quite different than these kind of throughput-oriented applications that we tend to care about and offline parallel algorithms. So I guess our goal is to explore this multi-SSD setting and see, exactly like you said, what applications do have limited performance loss when you translate them to this setting. So this is a kind of exploratory first paper, I would say.
Okay, thank you.
Thanks. Okay, so let me show you some cool stuff. So how do you actually build one of these systems? First you go buy a CPU. You buy a CPU with a lot of PCIe lanes. So let me give you a recipe for building one of these things. So we use one of these Threadripper CPUs. This is something called like a high-end desktop CPU. So it's not something that you would necessarily stick inside of like a server that's in a data center. It's something that you might buy for, it's like you can actually put it inside a desktop machine. And we bought a pretty reasonable amount of DRAM, so 0.5 terabyte of RAM. Yeah, it's high-end desktop instead of server grade. The total cost of our machine, everything, is under $10,000. Okay? And the majority of the cost is actually the chip, and then the SSDs. So we bought 31 SSDs, and these SSDs get attached to the platform using the PCIe interface. And I'll show you a picture of this on the next slide. It's very important that you buy a CPU that supports enough PCIe lanes. Okay, so in this one in particular has 128 PCIe 4.0 lanes. Each of those lanes gives you 2 gigabytes per second of transfer speed, of bandwidth. And so in principle, you might hope that you would get 256 gigabytes per second of bandwidth. Okay, so can you actually achieve that performance on a real machine? That's like the question. That's like what if you go read like the fine text, you're like, okay, maybe I can hope to achieve this, but do you actually get it? This is what this machine looks like. You attach the SSDs to the computer using something called a PCIe splitter. So each of the PCIe lanes are not exposed separately on the machine. They're actually exposed in 16x16 like width. Okay, so there's basically these big slots. And there's 7 of them on this machine, and so you need to bifurcate them in four ways. So each of these is using 4 PCIe lanes, each of these SSDs. And so you can stick most of your SSDs in there, like 28 of them in this way, and the remaining 3 you can actually place directly on the motherboard. So good, so we actually reserve 1 of these SSDs for the operating system, the remaining 30 are for experiments, and you get 7 gigabytes per second out of each of them. So maybe you can achieve like 210 gigabytes per second. Unfortunately, that's too good to be true, but Prashant, do you have a question? Yeah. It's a 64-core CPU. Yeah, good. Okay, unfortunately, no, you don't get 210 gigabytes per second of bandwidth. That would be incredible. Or RAM bandwidth is 145 gigabytes per second. So when we did our benchmark, we used this tool called FIO, written by Jens Axbo, a very nice tool to test I/O performance. And so what you see on this plot is as we go up the x-axis, you're increasing the number of SSDs. And on the y-axis is the bandwidth. So we keep getting linear scaling in the total bandwidth that we can push, but this scaling stops at about 135 gigabytes per second, and we can't go any higher. And we see a kind of similar trend for writes, but
it's like large blocks. This is best case, like large blocks.
Exactly, large blocks, like 4 megabytes per transfer. So what are the bottlenecks here? What are the bottlenecks that prevent us from getting higher performance? There's a couple of reasons. Well, one is that our machine actually has 145 gigabytes per second of memory bandwidth. That's the third row here. And so if you want to read data from SSDs, you actually had to move it from SSDs into DRAM. That costs something. You're using some of your DRAM bandwidth, right? So this is like an upper bound on the best SSD bandwidth you could possibly get. With FIO, there's some other overheads, so you're getting 135. And then when we actually wrote this ourselves, because FIO is kind of a synthetic benchmark, in our own library called Plaid, we wrote a reader, and it's getting about 120 gigabytes per second. And now there's a question. There's a lot of details that we can see in our paper. There's more reasons why there are bottlenecks. There's something called PCIe root complexes. You can see our paper for some details. But the question is now, can you actually get this bandwidth on a real-world problem, not this synthetic application?
Does this mean that if I want to build this machine again, I look at the main memory bandwidth and I don't buy more SSDs than
You're right. So I made a costly mistake. I think we're massively over-provisioned on SSD bandwidth,
okay.
and I'll explain that at the end.
You can buy 2 machines now.
Yeah, that's right. Or buy DDR5 or something. Get more memory bandwidth, so this is more balanced. Right? That was a mistake we made. Hopefully, you won't make it. Good, so let's look at another, like the simplest application you could think of. So instead of just reading data from SSDs and dropping it on the floor, let's think about like an application that's actually using the data that we read off the SSDs. So reduce. You're going to take the read and then sum up all the numbers. Okay? The in-memory version from Parallelism, it's getting about 120 gigabytes per second of bandwidth. And our external memory version, we wrote a very simple thing that just does the reads in large 4 megabyte blocks. And unfortunately, the bandwidth we get from it is just about 60 gigabytes per second, okay? Which is not bad, but it's maybe not as high as you'd hope. It's not 120 gigabytes per second. And the question is, well, why? There's still this 2x performance difference. So in the lower regions, this is probably due to like the overheads of initiating I/O. But as we're scaling the input size, why do we still have to pay this 2x performance difference? So let's look into that. And the reason is the memory bandwidth. And let's go in a little deeper into what exactly happens as we transfer reads from SSD to memory. So what does the in-memory algorithm have to do? It's got a bunch of data in DRAM. That data is not in cache. So it needs to basically do memory operations to move the data from RAM into cache. For the multi-SSD or an SSD algorithm, well, we actually had to do 2 memory operations per data that we're touching, per cache line. First, you had to actually read the data from disk into RAM, and this is done using something called DMA. So you basically, DMA, there's like an engine that's sitting there in hardware transferring data into RAM, and that's using up some of our write bandwidth and DRAM bandwidth. And then when the algorithm actually wants to do something with the data, you need to actually read it from RAM into cache. And so you're basically doing 2 memory operations per piece of data. And that's why we're getting about half the bandwidth of the in-memory version. But still, this 2x slowdown is not that terrible. Like maybe you're OK. If you can extend and actually solve problems at much larger scale, you might be OK with paying a 2x performance loss. And if you remember, I actually should have stressed this, we're actually able to scale this multi-SSD reduce all the way up to 8 terabytes of data on this machine. So the in-memory algorithm has to stop here. It can't process larger inputs because it's out of memory, but we're able to kind of gracefully scale our algorithm all the way up to like 8 terabytes of data. Okay. So let's look at a more complicated algorithm. Let's look at sample sort. And the characteristics for sample sort are quite different from reduce. Yeah.
The disk to RAM is lower, is higher than the time that you need to go from the RAM to cache. So I would expect a decrease that is higher than half, right? Than being.
But we have a huge amount of SSD bandwidth, right? So you're able to basically do this as fast as possible, as fast as your DRAM will allow it in some sense.
So the 120 that you said previously doesn't apply here, which was half than the.
I'm not sure I'm understanding your.
Yeah, it doesn't matter.
We can talk offline.
120 is about the same as the RAMs.
Jim.
So can you
Okay.
overlap the data movement from disk to RAM and RAM to cache?
We do. We're using asynchronous
okay.
I/O. We're trying to overlap it as much as possible, but this is the best we could get. If people work on this, I'd love to see someone overcome this somehow. Any other questions? Oh, I hope I'm doing OK on time. I'll try to go kind of faster, but please ask questions. So all of you have probably seen sample sort. Let me go through it quickly. There's like 3 things you do. It's like multi-pivot quick sort. Okay? You oversample some pivots from the data. You basically get B minus 1 pivots by oversampling. That defines B buckets. And then you distribute the keys to their corresponding bucket. This is like the shuffle or distribution step. And then you just sort the buckets in memory. Or you sort them somehow. You can do it recursively, or you can sort them in memory. Let's look at each of these steps in the multi-SSD setting. When you do this at like large scale, let's say 8 terabytes of data, you're going to need a lot of pivots. You're going to need on the order of like 60 or 70 or 100,000 pivots, let's say. Okay? And with oversampling, you're going to need to collect like millions of samples potentially. And each of these samples requires 1 disk I/O. So if you want to just retrieve 1 8-byte integer from disk, you're wasting a huge amount of your bandwidth. You're loading in at least 512 bytes of memory and just reading 8 bytes of it. And this is quite different from like the sequential scan and reduce, where you're reading in 4 megabyte blocks and you're using all of that data. So I just want to show you that small I/O is costly, but it's not terrible because SSDs are actually pretty good at they can support a large number of I/O operations per second. So we're running FIO, the benchmarker, with 4 jobs. And what you can see is that at smaller I/Os, you basically are paying a lot in terms of CPU overhead. The CPUs are really busy sending all these I/Os, and you're not getting much bandwidth. You need to go all the way up to like 256K or ideally on the order of megabyte level reads in order to saturate the bandwidth and also minimize the CPU overhead. And that's because these I/Os require more bookkeeping. And we're using actually the I/O U-ring engine for FIO. And that's something that's very important. I'm going to talk about that next. So we basically use this tool called I/O U-ring to kind of mitigate the CPU overhead of these small I/Os. Yeah, Prashant.
But with deeper queues, you can actually, with enough concurrency, you can convert lots of small I/Os into like high bandwidth I/O from SSD as well, right?
If you're doing like write combining or something like this, right? But here we're actually trying to just fetch completely random, non-write combine.
If you employ enough threads,
Yep.
and then the CPU visualization can be managed, and then those.
I agree, but you need to use enough threads, right? This is just using a handful of threads. If you use all the threads in your machine, there's a separate microbenchmark you ran that shows you can get like 27 million IOPS for 4K reads. And that's a setting that you're talking about, right?
In a typical setting like with threading threads or something, you can actually saturate the SSD bandwidth with enough thread, enough.
I agree. I agree.
Okay.
Yeah. So let me briefly go on a detour and tell you about IOU ring. What is IOU ring? It's a figure I stole from the web. IOU ring is another way of dispatching writes and reads to devices in external memory. And basically, the thing that kills you in terms of performance is the overhead of performing system calls. And IOU ring is a mitigation for, it's a like system, it's like a library, I guess, to enable you to perform a large number of IOs without performing as many system calls. And the idea is you use these ring buffers that are shared between the application and the kernel. And when the application wants to perform some IOs, it places its request inside of this ring buffer and then performs a single system call to tell the kernel that, hey, I have a bunch of IOs I'm trying to perform. So this lets you basically batch IOs. And so this can drastically reduce the amount of CPU time you spend performing system calls. That's really all I want to say about it. It's kind of tricky to program with. Probably LLMs address this somewhat. But yeah, there's a lot of footguns with like memory alignment and things like that with programming with IOU ring. So what is it? It's a new asynchronous IO interface. And it's for our throughput-oriented applications, it basically enables us to batch these IO requests. And as one data point for this micro benchmark, you can actually get 27 million IO operations per second. And this is kind of promising. I'll talk about this at the end of the talk. If you're trying to do like an irregular parallel algorithm, this is somewhat encouraging. This means that you can actually get quite a lot of random IOs for data that are potentially data dependent and still get good performance. Okay, so let's go through the next part of sampling. So sampling is handled. If you get 27 million IOPS, sampling takes like a negligible amount of time. You don't have to worry about it. Okay? What are the other steps in a sample sort? There's actually doing the partitioning. So for every element, you're basically going to binary search it into the pivots. And then you're going to kind of aggregate the data into these buffers. And once a buffer gets full, you send it to disk. Okay, so, but remember, how large should these buffers that we're buffering be? We said that we preferred large IOs over small ones. But if we make the buffers too large, there could be a large number of buckets. The total number of buffers is like the number of threads times the number of buckets, right? And if these buffers are large, they're 4 megabytes, we're going to run out of memory. So we don't want to do that. On the other hand, if you make the bucket buffers too small, you perform lots of small IOs. And you also have to contend with, like in our system, we're basically storing each of these buckets as a single file. So somehow you have to get these into a single file or have multiple files per bucket. So instead, we use this kind of 2-level scheme, which is pretty natural. If any of you worked on this, you would come up with this pretty quickly. So here's how it works. You read a large 4 megabyte read. This is the data that you're trying to partition. And then you assign it to the bucket that's supposed to go to. You have 4K buckets per thread. And then once you've filled up one of these buffers, you then send it to a global structure that's kind of aggregating these 4 kilobyte buffers per bucket. And then once you have enough of these, you then flush that. So I'm not showing that detail, but this is sort of an idea of some lower level details you might need to deal with when you're programming one of these systems. And there's some more figures and like similar I/O modules that we design that might be useful for other algorithms as well. So basically, we're adding like a small amount of synchronization overhead. We have this global structure, but it helps a lot because we can now have much smaller buffers and also scale to a large number of buckets without actually blowing up our memory budget. So finally, the last step, which is sorting in memory, very easy. You just read one of these buckets from disk, sort it in memory, and write it back to disk. And we have some other I/O modules that let you do this in a pretty clean way without worrying about too many of the low-level details. Overall, our sample sort code is about 100 lines. So we're actually abstracting out quite a lot of these multi-SSD details. And we are kind of programming at a reasonably high level of abstraction. Okay, so how does the algorithm perform now? Remember, it should be able to handle very large data sets and incur minimum performance loss. So here's our sorting results. You can see, again, there's some reasonably large overhead, like a 2 to 3x overhead at small scales, at 2 to the 30 input size. But once you get up to a pretty big input size, 2 to the 34, it's like 128 gigabytes of data, there's only a 20% difference in performance between us and the in-memory version. This is a highly optimized in-memory sample sort. Okay, so, and the in-memory algorithm cannot keep scaling, but our algorithm can. It scales all the way up to sorting 2 to the 40 8-byte integers. And that's exactly what we wanted at the start. So, one worry you might have, if you're hearing this, you're like, oh man, you build your own machine, you did all this crazy stuff, like surely this is incredibly brittle and fragile, and you're not going to be able to get this on other hardware, right? So a reviewer actually asked us that in the rebuttal, and we ran some experiments on a cloud machine. Luckily, there are machines of this form factor that look like multi-SSD machines out there. And so this is a machine called Google's C3 machine, and the cost to rent one of these machines with 32 SSDs is about $10 an hour, which is pretty inexpensive. Unfortunately, they only provide about 10 gigabytes per second of I/O performance, so they're under-provisioned compared to us, but maybe this is a better balance. It turns out this is actually enough for sorting, okay? And there's maybe some questions of why they have that provisioning. We could talk about that offline. So let's look at this performance scaling for these machines. So note whenever we go down a row, we're basically doubling the data size, okay? So first, observe that on our machine, which is this rightmost column, basically the running time more than doubles when we double the input size. But for the C3 machine, this doesn't happen. And that's because in our machine, we're actually CPU bottlenecked. So we have enough I/O bandwidth on this machine, but when we double the input size, we're more than doubling the amount of work that we do. But on the C3 machine, it's bottlenecked by I/O. But when you double the input size, you're only doubling the amount of I/O. So it gets basically linear scaling as one would expect. But our algorithm, without any modifications, runs on both these machines. And at the very large input size, it takes about the same amount of time. And there's not enough space on this C3 machine to actually run on the largest input size.
Question?
Yep.
So you're storing 8-bit integers?
8-byte integers. Yeah.
8-byte integers?
Yes.
Okay.
Thanks. Yeah, good question. Okay, so that's pretty much, I want to end with some musings on what to do next. Okay, so some takeaways. So in terms of how to bucket or categorize the applications we looked at today, if you read and do nothing, if you basically just transfer stuff from SSD into memory, you can basically saturate your memory bandwidth. And this is kind of what happens for sampling. And you get very high bandwidth. You're getting 140 gigabytes per second or something, okay? If you do some more lightweight operations, if you actually consume the reads, then you get between a third to half the performance of an in-memory only algorithm. And this is what you see for reduce. And this is like a memory bound or memory bottlenecked workload. Finally, if you have a CPU bottlenecked workload like sorting, you actually have very little difference between the performance of an in-memory and a external memory algorithm. And the exact amount of SSD bandwidth that you need kind of depends on the amount of parallelism that you have. And you should you should think about this more carefully. We'll do that in the next system that we build. So there's other results in our paper. We also show very similar results for random shuffle, actually permuting the elements inside of an array. And that's, if you think about external memory algorithms, a lot of them can be boiled down to shuffling. And we do fully general random shuffle with very high bandwidth. So that's promising. But there's also some other simple sequence primitives. So very quickly now, what's the right model? There's something called the parallel disk model from the 90s, okay? But that's a very synchronous model that basically says I want to issue P transfers to the P SSDs synchronously, one step at a time. Maybe it's reasonable to use, but I haven't seen much follow-up work on it since the 90s. So what do we care about? We want to model the usual things in a shared memory setting, work, depth, and also IOs now. But there are other desiderata. We want to distribute the data across the SSDs to avoid load imbalance. And maybe there's some ways to mitigate this by assuming some random load balance for blocks, if you can design your algorithm in terms of blocks. We also want to have high queue depth, and we also we prefer larger reads. There's a bunch of work on theoretically efficient parallel external memory graph algorithms. And it's really beautiful work, never been implemented to my knowledge. But maybe this multi-SSD setting is a good platform to try and implement this work. And a lot of the algorithms require the Euler-Tor technique, which can be kind of boiled down to sorting or permuting, and we can implement that. And kind of zooming out and thinking about desiderata for an external memory graph algorithm, doing a constant number of IOs per vertex seems like it might be okay if you have graphs with reasonable density. But constant IOs per edge is definitely too slow. If you have a graph with a couple of trillion edges, it's going to take a day or 2 days. And that's too long. I'm impatient. I don't want to wait a day to run an algorithm. And we should also kind of be thinking about richer algorithms and applications here. So far we showed that some kind of very simple primitives like sorting and permutation are also fast on multi-SSDs. And is the same true with graph algorithms? So there's some prior work that Julian and Guy and then myself did on Ligra and GPBS. Maybe we can take those algorithms. Those are very fast in shared memory settings. But maybe we can kind of build a different backend for them And using the fact that we can run a lot of I/O operations per second, maybe we can actually make these algorithms fast on multi-SSDs. And so we're working on this in like the semi-external version where you store the vertex data in memory. And I think it's very important to also, if you want to scale out like nearest neighbor search or bioinformatics, let's say you have data from a large collection of genomes and you want to index it, these are extremely data-intensive applications, and multi-SSDs might be a good fit for them. OK, so let me wrap up. So far, we showed that for problems with the right I/O patterns, we can do this. Okay? We can actually make them scale well on multi-SSDs. And they seem like a promising way to broaden the reach of single machine techniques. And these multi-SSDs are writing the current trends in hardware. PCIe bandwidth doubles per generation. We're going to PCIe 6 soon. We have a huge number of PCIe lanes per chips, and the SSD density keeps improving. And you aggregate, like bandwidth per core, not so good, but bandwidth per socket is improving per generation. So let's maybe try to build data structures, algorithms, and systems in this setting. And if you're interested in building one of these things, like let me know. I'm very happy to share what we know. Thanks. Any questions? Yeah, Jan.
Yeah, I have two algorithmic questions. The first one is for the sample sort algorithm. I think it's computational bounded, but it's also pretty much, I think, 50-50. It's also I/O bounded. But when we move it to the SSD part, do we change anything algorithmically so it make it more computational bounded?
We didn't have to change much. We did implement like heavy element detection. We like optimized the binary search quite a bit, but the high level algorithm didn't change, which is promising.
Yeah, so you also need one level sampling to fit in cache.
Yep.
So you jump over the memory part. So you have this one level and you fit in cache.
And you fit the pivots in cache, yeah.
In the calculation, it seems to be true. OK.
But if you scale the data up some more factors, maybe the pivots won't fit in cache anymore, and then you're in trouble, right? You might have to do this in 2 levels or something, recursively.
I see. So my second question is, I think you or we have the Sage work for semi-external, but that was for Optane. So now you move to SSD. Algorithmically, is there any major difference, or is more engineering work?
So far, it seems like it's more engineering work. That's my impression right now. Yeah, but that's a good question. Yeah, Claire.
So I know you don't want to do this, but since you're putting too much memory in the machine, right? Mm-hmm. So why not put it over 4 or 8 machines? And then have you thought about what the trade-offs would be there? I mean, obviously it's different programming model and everything.
Yeah.
But you could think about for $10,000.
You could
more
spread
cores,
this.
distributing it over that, and then what would happen?
Yeah, I think for the next revision of this, we definitely need to balance the cores, the memory bandwidth, and the number of SSDs per machine better. I don't. We do have some work on distributed algorithms. They're much more hairy, and unless you're running with very expensive networks, you end up being bottlenecked by network almost immediately. I don't know. It's an interesting direction to look into. Maybe multi. So first of all, I should actually say this is like a single socket machine. So just how to do multi-socket, multi-SSD. That's an interesting question, and then multi-machine is an interesting question too. Yeah, Phil.
So that rapid increase in price to get more and more terabytes on a single server. If I go to a disaggregated CXL-based system, is that going to actually just level off? Is it going to be more just whatever the cost of the DRAM that I add, and not like this ramp up? It seemed like you said you went from 12,000 to or 20,000 to 150,000.
Right. That was for the most expensive one. I mean, it is pretty smooth. I mean, the cost of putting DRAM on a machine, I guess you do get some linear increase as you make the DRAM chips themselves denser. So for I think you would pay less for a total 20 terabytes of DRAM, because you could use a less dense DRAM sticks. But it still wouldn't be that much cheaper I think. I think it would still work out to be about $100,000.
It's not just that you're paying this premium to get the premium version of their server.
Exactly.
It's just the raw cost.
It's the raw cost of DRAM. Even if you're using 32 gigabyte chip sticks, which are kind of inexpensive, they're still pretty expensive compared to SSDs. So if you can live with SSDs, you're better off doing that.
And I guess the energy cost is a lot better too.
Energy cost is a lot better. I didn't talk about that at all.
Having to refresh.
Exactly. Okay. Happy to talk to people.
Maybe we'll take more questions.
I'll take
One
more questions.
question or?
Are you
Take a break.
like running an independent file system on like each of these, or
We mount XFS on each of these.
independently?
Yeah, independently. And so we're actually programming with files. We didn't find that to have much overhead. If you want, you could try something like SPDK, or you could use block devices. Maybe you'll get some more performance, but yeah, XFS seems okay.
Maybe we'll take the rest of the questions offline.
Thank you.
Should be coffee, tea, either here or upstairs.